Hello everyone, we are from Group 6 presenting our design from methanol synthesis. And then, I will start by to introduce my members. I'm Kukaho, holding the matrix number of 193246, and this is my group members, Rafiq.
Hi, my name is Muhammad Rafiq. My memory number is 193437.
Okay, I have another group member which is Aina. Aina?
Hi, my name is Noina Shafika Binti Wakari. My matric number is 194892.
Okay, actually we have another group members. He's not available because of his own personal reasons. So three of us are going to present the videos today. And so the objective of our methanol production is to have a purity of methanol which is 60%, and then our raw material is from coal, and then our capacities which is the production rate is to produce 380 million metric ton of methanol per year, and then our operating period is 330 days. The method is to react carbon monoxide and hydrogen gas to produce methanol, which is seen in the methanol production blocks. And then these are the blocks that we are going to use for our methanol synthesis. We will start off by using gasification and an acid gas remover to remove the unwanted gas, and electrolyzer to produce hydrogen gas, and then methanol synthesis, which is the most important block, and then topping, and finally mixers to produce our desired purities. So we will start off by our gasification process. So this is okay, so this is the gasification process we have, and then so we will start off by our gasification block. So as you can see, in the gasification we have the ultimate analysis of coal, and then you can see that this is the difference between the mole fractions of carbon between the volatile carbons and the fixed carbons. And actually the fixed carbon has greater mole fractions than the volatile carbons. And another thing is that we will have another input, which is oxygens plus the stream of waters in the form of steam, which is very hot. And then to react with oxygens, water with carbons, we actually will have two reactions. As you can see from this, we have two reactions. Carbon will react with oxygen to produce carbon monoxide. Carbon will react with hydrogens to produce carbon monoxide and hydrogens. And based on two of these equations, we actually limit the amount of oxygens and hydrogens so that we do not have additional reactions such as the productions of carbon dioxide. And then based on these calculations, we know that 50% of the volatile carbon will follow the first reaction, which is the production of carbon monoxide, and the another one will follow the reactions of the second reactions, which is to produce carbon monoxide and hydrogens. And then this involves the volatile reactions, and then finally we have slag going out at the bottoms, which include the fixed carbons that we do not want. And in the acid gas remover, we have the stream from gasifications, and also we have another streams of strippers, which is our solvents. And this block is to remove the unwanted products that we do not want, like hydrogen sulfide, and then to get the streams that we want, which is of these four components. Another thing from the acid gas removal part is that we actually assume that 100% of hydrogen sulfide will come out of the streams that we do not want, and then we can remove 100% of hydrogen sulfide. And we also assume that the basis for stream number 5, which is the streams of our solvent. And then yeah, after doing all the balances, we'll get the answer. So the important part is in this is just the portions of how much solvent that we use.
Okay. In methanosynthesis, we have two streams. Stream 1 is from the acid gas removal, and stream 2 is from electrolyzer. Okay. We will discuss about stream from acid gas removal first. Okay. From we can see that the amount of carbon monoxide here is higher compared to the uh, amount of H2 in the stream. From the stoichiometry, the amount of hydrogen needed to convert to react with carbon monoxide to convert to methanol is higher. So we need another source to get more hydrogen. So we will do electrolyzer. This electrolyzer process is we put water and dissociate it into oxygen and hydrogen. So from stream outlet from the electrolyzer we get hydrogen. We put it into the methanol synthesis. So we can increase the number of hydrogen input to the methanol synthesis to increase the production of methanol. So
Okay, so now we are at the topping column where the flow rate from the methanol synthesis is approximately 70,000 million mole per hour, and the solvent is dimethoxyethane, which is approximately 56,000 mole per hour that flow through the topping column, and then there's a two product which are the gas and the liquid. For the gas is the flow rate is approximately 49,000 million mole per hour, and for the liquid product is approximately 12,000 million mole per hour. And the composition for input uh, the input from methanol synthesis is 0.6 mole methanol, 0.1 mole water, 0.03 mole oxygen, and 0.253 mole carbon monoxide. And since the solvent is we use dimethoxyethane, so it's a pure, so it's a 1 mole. And for the gas product, we got 0.115 mole oxygen, 0.884 mole carbon monoxide, and 0.01 mole dimethoxyethane. And for the liquid product, we get 0.85 methanol and 0.15 water. So the liquid product from the topping column, we flow it through to the mixer. So in the mixer, the flow rate is approximately 12,000 million mole per hour, and we mix it with the water, so we get the purity that we want, which is 60%, at least 60%. So the flow rate of water we put into the mixer is approximately 51,000 mole and million mole per hour. And in the mixer, the product we got is the molar flow rate is approximately 17,000 million mole per hour, and the the composition of the methanol we got is 0.6 mole methanol and 0.4 mole water as we want. The purity is 60%. Okay, so that's all. Thank you.
We are costing part and our feed is coal. Price of coal is 310 ringgit Malaysia per ton, and we use approximately 619 million ton per year. So we times with the price and we will get 192 mm, billion ringgit Malaysia per year. And for the product methanol, the price is uh, approximate 57,000 per ton, and the and we use uh, and then we use about 418 million ton per year, and when we times we will get approximately 24 trillion ringgit Malaysia per year. And for the solvent dimethylamine and dimethoxyethane, for dimethylamine is 40.8 ringgit Malaysia per kilo. So we use around 87.1 kilogram per year. So we times it, we will get around 356 billion ringgit Malaysia per year. And for dimethoxy, we use about 4, 400 400 million kilogram per year, and we times with the price, we will get around 186 billion per year. So the total cost we is the methanol profit minus with the cost of coal and cost of solvent, we will get approximately 9 trillion ringgit Malaysia per year. Okay, thank you.
Back, as a conclusion, these are the recommendations to generate more product and to be more flourish in our cell. So yeah, the waste product can be recovered and sold as a product, such as product as sulfur. The waste product H2S is actually wasted and should be recovered back. And another thing is that the remaining coal can be recovered as well, because the rest of the coal is going to be wasted as slag, which is not good, and then it can actually generate more methanol by undergoing combustion, or to be sold as a tar, to be recovered back as a tar, which can generate more income for the company. So another thing is that the stripping using methylamine, CH5N, and methoxic ethane can be recycled using absorber. As you can see that dimethyl dimethoxyethane is very expensive, even more expensive than coal, and recycling can save major costs for our commodities. And the costing part, we didn't take water into consideration of the cost, because we take it as the cost under machinery. And yeah, so we consider it as free, and the maintenance it cost is actually the cost that we do not take in. And the calculation does not include the cost of plant itself, modification and improvement, engineering, construction costs, and contingency costs. So it's actually accounting the feed and the product itself. So it's very simple. Yeah, so that is our conclusion for our methanol synthesis.